Banthiya and you are watching Banthiya's Training in Consultancy. And we are looking at Introduction to Organic Chemistry, a very important chapter in chemistry. If you haven't seen the last chapter, please find the link that is coming above. Let's begin the second chapter of this, that is Nomenclature of Organic Compounds. Nomenclature of organic compounds is very important. And before we do that, let's understand a couple of basics. Allotropes of carbon. The element carbon occurs in different forms in nature with widely varying physical properties. The physical properties are widely varied here. The difference lies in the manner in which the carbon atoms are bonded to one another. For example, let's take diamond and graphite. So, in diamond, each carbon atom is bounded to 4 other carbon atoms forming a rigid 3-dimensional structure, whereas each carbon atom is bonded to 3 other carbon atoms in the same plane, giving a hexagonal array in which one bond is double bond. So here we have a single bond to all the 4 carbons, and in graphite we have a hexagonal array. Diamond is the hardest natural material that we know, and graphite is slippery because, as we have seen, that diamond is a 3-dimensional structure, whereas graphite is planar structure. So the layers can slip over each other, and as a result, diamond is a bad conductor of electricity, whereas graphite is a very good conductor of electricity because one bond is yet to be done. That is, there is one valence electron present in that. Let's see something more about allotropes. So diamond can be synthesized by subjecting pure carbon to very high temperatures and pressures, and such synthetic diamonds are very small in size, but they are indistinguishable. That is, they cannot be differentiated from the original diamonds that we know. Fullerene is another allotrope of carbon. The first one to be identified was C60, which has carbon atoms arranged in a shape of a football. Since this looks like geodesic dome designed by the US architect Buckminster Fuller, the molecule was named fullerene. So these are the structures given here. So in this structure we have 6 carbon atoms in a hexagon and one bond, that is only 3 carbons are attached. One loose electron is present which loosely attaches these 2 molecules, that is planar molecules, to one another, and they are free to move, and that's the reason they are good conductors of electricity. And as we have already seen, diamond has a 3-dimensional structure, and fullerene is like a football which is composed of pentagons and hexagons. Now let's see skeletons. So skeleton, there exist 2 possible carbon skeletons for 4 carbons, and this is what they are. So 4 carbons can be arranged in a row, straight chain, or a branched chain. So they are called skeletons. They are having same molecular formula but different structures, and hence their properties will vary. Such compounds with identical molecular formula but different structures are called structural isomers. In addition to straight and branched chain carbon chains, some compounds have carbon atoms arranged in the form of a ring, and that we have already seen in lecture 1. For example, cyclohexane has formula C6H12 and all the valencies of carbon are balanced here. Straight chain, branch chain and cyclic carbon compounds all may be saturated or unsaturated in a skeleton. That is, there can exist a single bond, double bond or a triple bond depending on the molecule. So an example to this is benzene, that is C6H6, and this is a resonating structure of benzene that we will be studying later on. Heteroatoms. In the last session we have seen that are those which contains only carbon and hydrogen in them, but when the atoms other than hydrogen when comes into play, that is, they are attached or substituted by another atom, they are called heteroatoms, and they may be halogens, oxygen, nitrogen and sulfur. In a hydrocarbon chain, one or more hydrogen can be replaced by these elements such that the valency of the carbon remains satisfied. Here, this is one of the most important points, that is, the valency of carbon remains satisfied. If the valency is not satisfied, then the compound will not be stable, and we want a stable compound. In such compounds, the element replacing hydrogen is referred to as heteroatom. Now that we have understood what heteroatoms are, let's see functional groups. So functional groups and the group containing this confer specific properties to the compound regardless of the length and nature of the carbon chain and hence called functional groups. Basically, they confer specific property. What do you mean by a specific property? That is, their property will change because we have added something to that, regardless of the length and the nature of the carbon chain. That is, it may be branched, it may be straight, or it may be cyclic. But when you attach a heteroatom to a carbon molecule, carbon chain, then its basic chemical properties will change, and hence they are called as functional groups. Free valency or valencies of the group are shown by a single line, and the functional group is attached to the carbon chain through this valency by replacing one hydrogen atom or atoms. That is, carbon has 4 valencies, and we already know that. So these 4 valencies can be satisfied with hydrogen. But in case if we want to replace one hydrogen with say chlorine, as chlorine also has single valency, so then it is univalent, and that's the reason we can replace hydrogen with chlorine, and here chlorine will be called heteroatom, and generally we represent chlorine as -Cl, which represents the single line, that is the valency. Heteroatoms, this is the list. As we have already seen chlorine and bromine, they are called, their functional group is called halo, that is chloro, bromo, iodide, etc. And formula of the functional group is -Cl, which represents a single bond, and -Br, which also represents a single bond, and they substitute hydrogen atom in a carbon compound. When we want to use oxygen as a heteroatom, these are 4 things that we are gonna study in this chapter. That is alcohol, aldehyde, ketone, and carboxylic acid, which has functional group as OH, CHO, C double bond OC, that is, and both the ends, both the valencies can be satisfied with another carbon or hydrogen. In case we have used this carbon with hydrogen, then we get aldehyde, and when we replace this carbon with OH group, then we get, that is, carboxylic acids. So these are 5 functional groups that we are going to study in this chapter. Homologous series, a series of compounds in which the same functional group substitutes for hydrogen in a carbon chain is called a homologous series. That is, when the series of alkanes in which one hydrogen is replaced by a OH group, that is an alcohol group, they will be called as a homologous series. For example, the chemical properties of CH3OH, C2H5OH, C3H7OH and C4H9OH are all very similar because their functional groups are the same, and we have substituted one hydrogen atom with OH group here. As the molecular mass increases in any homologous series, a gradation in physical properties is seen. That is, a slight variation, a slight change is seen in the series. This is because the melting and the boiling point increases with the increasing molecular mass, and as it is a very fundamental concept of chemistry. Other physical properties such as solubility in a particular solvent also show a similar gradation, because as we know already that when the molecular mass of a compound increases, its solubility tends to decrease, and this is a general rule. But chemical properties which are determined solely by the functional group remain similar in a homologous series, and hence they are called homologous series. So these are the examples. Alkanes, they all have single covalent bond, and hence they form a series. For example, methane, ethane. Alkenes, they form double bonds, and hence they also form a series. Alcohols have OH as a functional group, and hence they form a homologous series. Similarly, carboxylic acid has a functional group COOH, and hence they also form an homologous series. For example, methanoic acid, ethanoic acid, butanoic acid, and so on. So finally, now that we have learned a couple of more basics in carbon compounds, let's see how nomenclature is to be done. That is, how we are supposed to name carbon compounds. Nomenclature of carbon compounds. The names of compounds in a homologous series are based on the names of the basic carbon chain. Basic carbon chain, we have already seen what does this mean in the last session. And if you haven't seen yet, then please pause this video, go back to the first chapter, and in case you have any doubts, please feel free to comment in the comment section below. The base carbon chain, that is, if there is one carbon, we say it as met. If there are two carbons, we say it as eth, 3 prop, 4 but, 5 pent, 6 hex, 7 hept, 8 oct, 9 non, and 10 dec. And these root words, that is basic carbon chain, are modified by a prefix or a suffix indicating the nature of the functional group that is present. For example, in alkanes, as I have already pointed in the last session, that in alkanes we put the suffix that is ane, and hence we get methane, methane, and ane is the suffix that we use. Similarly, in alcohols we used ol as a suffix to a alkane, that is a base. With the help of IUPAC system, we need to do the nomenclature, that is the naming of carbon compounds. What is IUPAC, by the way? IUPAC is International Union of Pure and Applied Chemistry. It says that first you need to get a root word, and you may either attach a suffix or a prefix depending, or you may have to use both at the same time. The suffix can be primary suffix or a secondary suffix. Primary suffix generally says nature of the carbon chain, that if it is branched, alkane, alkene, or alkyne. Secondary suffix generally states the functional group or represents the functional group, and the prefixes may be the branched, a specific branch that we have to name, or the number to which the functional group is attached, or the halo group. It may be anything, but these are various tools that we have to use. Let's see how. Naming a carbon compound can be done by the following methods. First is identify the number of carbon atoms in a compound. This will give you the root word that we are supposed to use. Here, one more important thing is you have to choose the longest chain. In case a functional group is present, it is indicated in the name of the compound with either a prefix or a suffix, and that will depend on what the rules say. If the name of the functional group is to be given as a suffix and the suffix of the functional group begins with a vowel, suffix of the functional group begins with a vowel. For example, alcohol, we have seen OL, so it begins with a vowel O. Then the name of the carbon compound, carbon chain, is modified by deleting the final E and adding the appropriate suffix. For example, we have propanone. Propanone is a ketone, and we have already seen ketone. Ketone is this functional group. So here propane and ONE. So ONE is the suffix for ketone, and propane, PROPANE. So that E is deleted there. And the final rule is, if the carbon chain is unsaturated, then the final ane in the name of the carbon chain is substituted by ENE for double bonds and YNE for the triple bonds, and we have already seen this in the last session. So in a nutshell, this is the summary, that is for haloalkanes. Now the point to be noted here is we are talking only about the alkanes here. So haloalkanes, we put a prefix chloro or bromo. For example, chloropropane or bromopropane. For alcohols, so as we have already seen, OL is attached. For aldehydes, we attach AL, and the functional group for aldehydes is C double bond O single bond H. Ketones is ONE, that we have already seen, and its functional group is double bond C double bond O. Carboxylic acid, that is oic acid, so functional group is C double bond O, single bond OH, and this forms carboxylic acids. Alkenes are double bond and alkynes are triple bond, and we already know this. So these are the basic list of nomenclature, and these are most fundamental nomenclatures that we have to look at primarily. Now let's see a couple of examples based on this. Draw the electron dot structure of ethine and also draw its structural formula. Now ethine, so YNE means triple bond, and eth is the functional group used for 2 carbons. So we have C triple bond C. Now we are left with 1,1 valency. So we put hydrogen because it is an hydrocarbon, and we get this to be the structural formula. And the electron dot structure would be one carbon will share 3 electrons with other 3 electrons of another carbon, and 1 electron of a carbon with 1 hydrogen atom, and another carbon atom will share again similarly 1 electron with another hydrogen. And that's your final answer. Now let's look at another example. Write the name of the following compound. It's a branched hydrocarbon that we can see because we have 1 carbon, 2 carbon, 3 and another carbon attached to carbon number 2. And in this case, the longest chain would be maximum for 3, and 3 means prop. And this is a alkane, so it would be propane. And here we have to give the list number to the branch, that is 1, 2, 3 or 1, 2, 3. By default the list number comes out to be 2, and hence we say 2-methyl propane. The final answer is 2-methyl propane. Here methyl comes from this single carbon, and YL is the suffix used for a branch. You need to memorize this, that YL is the suffix. So 2-methyl propane is the IUPAC name for the given compound. Let's see the next one. Similar question, 1, 2, 3, 4, 1, 2, 3, 4. So we have 4 maximum, so it will be butane because of 4 carbons. And now trying to give the lowest number, 1, 2, 3, 4 or 1, 2, 3, 4. So by default it comes 2, 3. So the name would be 2, 3. This is a methyl group and this is also a methyl group because 1 carbon is at the branch. So it will become di-methyl butane, and this will be your final answer. Let's look at the next question. Again this is a branched carbon chain, but let's see which is the longest chain. So this will be 1, 2, 3, 4. Okay, now this can be 1, 2, 3, 4, 5, 6. So I guess 6 will be the maximum, and 6 is for hexane, and we already know that. Now let's see if we can put the lowest number to this branch, that is methyl group. So from this way 1, 2, 3, 4, so the number would be 4. And if we start giving numbers from the lower end, 1, 2, 3, 4, 5 and 6. So this will be the smallest number, so we will use 3. So the name becomes 3-methyl hexane, and this will be your final answer. Now let's look at the next. Here we have double bond and a branch as well. So another rule here is that the functional group needs to be given the smallest number. So we start here with 1, 2, 3 and 4. So 4 means butane. It is a double bond, so but 1 ene. Ene is the suffix for double bond, that is alkene, and we have a carbon attached to the third carbon, that is then becomes 3-methyl but 1-ene is the final answer. Now let's look at the next question. It is a triple bond now, and we have to give the lowest number, so we'll start numbering from 1, 2, 3, 4, 5 and 6. So 6 is hexane, but in case of alkynes we put YNE as the suffix. So this becomes hex, carbon is second, YNE, and the methyl group is attached to fifth carbon, so it becomes 5-methyl hex to YNE, that is hexine. Now few students ask me that why 2 should be written and not 3, because the third carbon as well has a triple bond, that is it shares a triple bond. But as we know, the rule says the lowest number should be assigned, and that's the lowest number. Now let's see the next question. Here a chlorine group is attached to the third carbon. Either way it is a third carbon and it is a alkane, so it becomes 2-fluoropropane. That's your final answer. Now next question. Now that's a bit complicated question. Bromine, bromine and fluorine. Let's start numbering them. 1, 2, 3, 4. And in the reverse way, reverse order, 1, 2, 3, 4. Now the point is we have to start from here because the functional groups has the maximum number 3 in this case. Whereas when we take from the other end, the maximum number becomes 4, and as the rule says, it should be assigned the lowest number possible. So it becomes 1, 3 dibromo. Now D alphabetically comes before F, and hence we write bromo first. Then 3-fluoro, and we have 4 carbons, so it's an alkane single bonds, so it becomes butane, and that's your final answer. Now let's look at the next question. Here OH group is attached and to the second carbon, obviously because from this end it will have a larger number, so we have 5 carbons, so it becomes pentane because of 5 carbons, but here we cannot write E, so it becomes pent-2-all. That's your final answer, and you can as well represent this as 2-pentanol. 2-pentanol. This is also right method, but I would prefer, or I would suggest rather, to use this method, because when the nomenclatures become complex, then it will help you. Now next question. Now CHO group is an aldehyde. One more thing to note about aldehydes is that please note the valencies of this carbon. It has 1 attached to hydrogen, 2 attached to oxygen, and it is only left with 1. So aldehydes, that is CHO group, that is the functional groups of aldehyde, will always be attached to one of the ends of the carbon chain. Now that we know this, we need not to denote the number of carbon. So we can start with 1, 2, 3. We have 3 carbons, so it becomes propanal. It becomes propanal. Al is the functional group of aldehydes. Now next question. Here this is a ketone group. 1, 2, 3, 4. It is an alkane, so it becomes butane, and the last E should be deleted because of ONE, so it becomes but-2-all. own. That's your final answer. Next question. Again, this is an ketone and it's a branch chain. So 1, 2, 3, 4. So it becomes 3 methyl 3-methyl butane-2-one. Now let's see the last question. Again, and we have already seen this. Now first of all, let's focus on the valency of carbon. So one is attached to oxygen, the other two is attached to another oxygen, and we are only left with one single bond. Hence, carboxylic acids, the functional group of carboxylic acids will also be towards one of the ends of the carbon chain. So it becomes 1, 2, 3, 4, 5, and it's an alkane. So it becomes pentanoic acid. And that's your final answer. I hope guys that you have understood the concept of nomenclature, and in case you have any doubts, please them with me in the comment section below. And if you haven't yet subscribed to my channel, please do that. Like it, share it and subscribe it. And please don't forget to press the bell icon if you don't want to miss any updates from my channel. Thank you for watching this. Thank you.